everyone, in this video we are going to present evaporation of food calculation. So now let's see an example, single effect evaporator to find the steam usage and heat transfer surface. A single effect evaporator is required to concentrate a solution from 10% solid to 30% solid at the rate of 250 kg of feed per hour. If the pressure in the evaporator is 77 kPa absolute and if steam is available at 200 kPa gauge. So now we are going to calculate the quantity of steam required per hour and the area of heat transfer surface if the overall heat transfer coefficient is given. In this case, we are going to assume that the temperature of the feed is 18 degrees Celsius and that the boiling point of the solution under the pressure of 77 kPa absolute is 91 degrees Celsius. So assume also that the specific heat of solution is the same as the water, and the latent heat of the vaporization of the solution is same as the water under the same condition. Now let's start our calculation. Before that, we need to find out all the information from the steam table. The condensing temperature of steam at 200 kPa gauge, known as 300 kPa absolute, is 134 degrees Celsius, and the latent heat will be 2164 kJ per kg. Next, the condensing temperature at 77 kPa absolute is 91 degrees Celsius, and the latent heat is 2281 kJ per kg. Based on the mass balance, we know that the feed rate is 250 kg per hour, and then it consists of 10% solid. Refer back to the question, we need to concentrate a solution from 10% solid to 30% solid. So in final product, we will consist 30% of solid, and then the 70% will be the liquid, so total will be 83 kg per hour. Therefore, the mass balance will be 250 of the feed will minus the product outlet 83, so the total evaporation rate will be 167 kg per hour.
To calculate the quantity of steam required per hour, first we need to find the heat available per kg of steam. The equation used to calculate the heat available is latent heat plus sensible heat in cooling. At 200 kPa, the latent heat of steam is 2164 kJ per kg. This latent heat is added with the sensible heat in cooling, where we use the heat capacity times the temperature difference between 134 degrees Celsius to 91 degrees Celsius. Then the heat available is 2.34 times 10 power of 6 joule per kg. Now, we need to calculate the heat required by the solution for evaporation. We can use the same equation to calculate. The sensible heat in heating the solution from 18 degrees Celsius to 91 degrees Celsius is calculated by using the heat capacity multiplied with the temperature difference, and it needs to be multiplied with 250 kg per hour, which is the feed of the solution. This sensible heat is added with the latent heat of steam at 77 kPa and timed with 167 kg per hour, which is the amount of solution evaporated. The heat required by the solution is 4.57 times 10 power of 8 joule per hour. As we know that the heat from steam is equal to the heat required by the solution, by dividing the heat required by the solution with the heat available of the steam, we get the quantity of steam required is 195 kg per hour. By dividing the quantity of steam with the amount of solution evaporated, we can know that 1.17 kg of steam is required for 1 kg of water evaporated. To calculate the area of heat transfer surface, we can use the heat transfer equation. As we know that the temperature difference across the evaporator is 43 degrees Celsius, by substituting all value into the heat transfer equation, we can get the heat transfer surface, which is 1.74 meters square.
Now come to the next example, triple effect evaporator to calculate the steam usage and heat transfer surface. A triple effect evaporator is used to evaporate 500 kg per hour of a 10% solution up to 30% solution. Steam is available at 200 kPa gulf and the pressure in the evaporation space in the final effect is 60 kPa absolute. In this example, we are going to assume the overall heat transfer coefficient are 2270, 2000 and 1420 joule per meter square per second per degree Celsius in the first, second, third effect respectively. And we also ignore the sensible heat effect and assume there are no boiling point elevation and assume equal heat transfer in each effect. Now we start our calculation by constructing a mass balance table. Based on the information being given in question, the feed rate of the solution is 500 kg per hour, and we know that we need to evaporate a 10% solution up to 30% solution. So the final product will consist of 30% of solution. The total will be 167 kg per hour. The total evaporation rate will equal to the difference between the product outlet and the feed outlet, which is 500 of the feed minus 167 kg per hour equal to 333 kg per hour.
To calculate the heat balance, we can get the conditions from the steam tables, which the condensing temperature of steam at 200 kPa is 134 degrees Celsius and the latent heat is 2164 kJ per kg. Evaporating temperature in final effect under the pressure of 60 kPa absolute is 86 degrees Celsius, as there is no boiling point rise and latent heat is 2294 kJ per kg. By equating the heat transfer in each effect, Q1 equals to Q2 equals to Q3. I got this equation below. And dt1 plus dt2 plus dt3 is equals to 134 degrees Celsius minus 86 degrees Celsius, and you can get 48 degrees Celsius. Now if we assume that A1 is the same with A2 and A3, so that we can get dt1 times 1 plus U1 over U2 plus U1 over U3 equals to 48 degrees Celsius. By substituting the overall heat transfer coefficient of U1, U2 and U3, we can get dt1 equals to 12.9 degrees Celsius. And we can solve the following for the dt2 and dt3 to get their respectively temperature. By equating the quantities evaporated in each effect and negating the sensible heat changes, if W1, W2, W3 are the respective quantities evaporated in effects 1, 2 and 3, and Ws is the quantity of steam condensed per hour in effect 1, then we get this equation: W1 times 2200 times 10 power of 3 equals to W2 times 2240 times 10 power of 3 equals W3 times 2294 times 10 power of 3 equals to Ws times 2164 times 10 power of 3. The sum of the quantities evaporated in each effect must equal to the total evaporated in all three effects, so that W1 plus W2 plus W3 equals to 333, and solving as above, you can get W1 equals to 113 kg per hour, W2 is 111 kg per hour, W3 is 108 kg per hour, while for the Ws is equals to 115 kg per hour. For the steam consumption, it required 115 kg steam to evaporate a total of 333 kg water. That is 0.35 kg steam per kg water evaporated. By writing a heat balance on the first effect, we can get the heat exchanger surface. So we can get the total area is equals to 7.2 meters squared. Note that the conditions of this example are simplified, that the sensible heat and feed heating effects are neglected and there are no boiling point rise occurs. The general method remains the same in the more complicated cases, but it is often easier to solve the heat balance equations by trial and error rather than analytical methods, refining the approximations as far as necessary.